All right. Welcome back, everybody. I think it's time to start the second lecture. Right, today we are going to talk about Gaussians. I'm sure that this is a topic familiar for most of you, but you will see that we'll be studying them on particular topics, which will be interesting for the state estimation problem. Before starting with this, let's do a quick summary of what we did yesterday. So if you remember, well, apart from talking about the logistics on the course and all these things, right, which, by the way, are in Canvas, we also start discussing some content on the course, right? So we started with the expectation operator, right? We gave some examples, some properties. You will see these today and in the next days, so it's something that will just appear. But yesterday we did the proper definition. The same happens with the term covariance, right? And also, well, mean, but I'm not writing it here. So we started defining the scalar form, right? But at the end, eventually, we'll be more interested in the vectorial form of covariances. We discussed some, well, properties of it, right? So the first one is, so just by construction, this is symmetric. And the second one is that it's going to be positive semi-definite. If we have done things correctly, it should be positive definite. But strictly speaking, there might be some zeros there. Okay, so what else? We also discussed a little on the sample mean and sample covariance. Remember, we were just sampling these are our samples, right? And they were drawn from this distribution. And the idea was, okay, so if you get enough of these samples, can you calculate, can you estimate, although you don't know this distribution, can you estimate the mean and covariance, right? And we gave just a closed form for it. So I think this is the summary. Did anyone check problem set 1? Okay, so we have already, I think with maybe with what you know from before, you can do it, but just with yesterday's explanation, it's probably a little, well, not enough. I think with what we explained today, you will be ready to finish almost, yeah, more than half, maybe. So my advice is, now that you have fresh things, fresh ideas after coming to class, start working a little on the problem set, right? Take a look, because, well, it's better now than last minute. Okay, so as I said, today's topic is going to be on Gaussians. So let me just start with the well, definition, in this case on a single variable, right? I'm talking here about distributions, right? But in general, or let's say that the more correct name will be probability density functions. But we'll be using these two terms on the course they are equivalent, right? It's simply, I guess, more convenient to talk about distributions, but actually these are PDFs, right? In the sense that, well, if you have seen the review on probability, well, there's a explanation for all this, but I guess this is familiar, right? So, okay, so this is a well-known formula, right? It has we'll see so there's this term here at the beginning, which, well, you can't remember or not. And then this is the most well-known part, right? So this is for just a one-dimensional variable. In this case, x, it's just a scalar, right? And then this part, that's what I was saying, that this actually is the normalization factor. and the only reason is just to satisfy the total probability law, right, that we also defined yesterday. So, okay, this can be just a number to make sure that then when we do the integral, right, on the full range of this function, the result is 1. Yeah, by the way, also, I didn't define it, but we can define Gaussians. They are also known as normals, right? And a way of just, because I'm not going to write this term all the time, right? This exponential, this is a little tedious, so it's simply this kind of archaic n with the variable, the state variable, and then mean and variance, right? Also, here there's a difference. So in this case, sigma is the standard deviation, but here on the definition, we are always going to be using variances, right? For multi-scale, for multidimensional, you will see that we'll be using covariances. Okay, so, right. This is the compact definition for us, this n. So, now again, I'm just gonna plot, or I'm gonna try to plot. Yes?
Just for not misunderstanding, inside the parentheses, we have inside this for sigma not over 2, is that when it's over, are they the same or?
Yes, wait. You mean this?
Yeah.
Yes. Yeah, so it's the same, right? So it's always mean and variance. Okay, good catch. So now let's try to sketch a plot of this. So just by construction, we know that there's going to be symmetries, right? Because it's the exponent is a square. But exactly how does this look like? Okay, maybe. Okay. Okay, so an interesting property of this is that mean, right, it's the maximum, right, and it's also the mode. It's also the median, right, so on Gaussians we have all these nice properties that exactly these three values are the same. It's not the same, it's not true for other distributions, and we'll see that actually this will help us later when we do estimation, right, so this is an interesting property, I would say. Right, so here I'm writing here this again. Okay, so what else do we know about this? So usually the standard deviation, it's an important value, right? So this is a square, we need this on square form for estimating, for calculating values, but actually it has a physical meaning, and one dimension it's very clear, right? So we usually talk about one standard deviation, and why is that? Because here in this 1 sigma region, actually there's a lot of probability mass contained, right? For 3 sigma, this is almost, and one-dimensional, this is almost 99%, right, of all the probability mass on this distribution. So what is this telling us? That it's very unlikely that you find like a value or you see an observation that is outside 3 sigma. So it's possible, but very unlikely. Okay, so also for hypothesis testing, we'll see that this can be useful. But, well, there's also like a problem in problem set 1 that you will be required to be plotting like 1 sigma or 3 sigma of the distribution, right? So you will see this in action when you start doing the problem set. Has anyone finished problem set 1? No, okay. Yeah, you shouldn't. Wait, you finished? Oh, okay. Okay, and then we have also the cumulative distribution function. I'm just referring to this because the other PDF can be a little misleading. But, well, basically, this is the integration of PDF, right? And we are not going to use like cumulative distributions a lot, but it's something for you to know, right? And here we have 1/2, and we know that this should converge to 1, right? Okay, so known things about Gaussians, but I think the most important one is you get this idea, right? So it's this kind of symmetric function where mean, median, okay, doesn't want to work now, and mode are the same, right? So okay, so now let's define mean, right? We know that we gave a definition yesterday, so no surprises. Here the expectation operator comes again. And basically, well, I'm just writing here the definition, but I have already said that mean, well, it's this. So if you see on the definition, this is one of the parameters that we need to express a Gaussian. And the second and only parameter that we need is the variance, right? And we also defined this yesterday. Okay, so what is the interesting thing about this? That with only these two parameters, right, we can exactly determine a Gaussian. So it's going to be easy for us. It's not like any exotic distribution where we need, I don't know, 10th order moment. I mean, of the order, it's on the expectation. But we just need the first order and second order, right, which correspond to the mean and covariance. So with this, these are all, oops, all required parameters. Okay, another interesting, or notation that we are going to be using is most of the times we are going to be drawing samples, right? So let me just write it like this, right? In this case, x, well, it can be a sample, x sub I, and we are going to be using the same notation as before, right? You can use the variable or just write here the mean and covariance, right? But the thing is that we know that this corresponds to the normal distribution. Most implementations now I'm talking about software, they have an implementation for random numbers, right? And I guess you already know that this corresponds to this, right? So when you go to your random number generator, normal one, it's zero mean and covariance 1, right? So this is ready. Do you have like other covariances, other things? Well, it depends, right? There are functions that, yes, they hold this, but, well, this is the most standard one. Okay, so this is just a one-dimensional thing. I think everyone was like familiar already with Gaussians, the definition. This has been in many courses, right? Okay, okay. So now let's go, yes? No, it's a sigma, but maybe, okay, yes. But don't worry, because this is the one-dimensional case. For the multi-dimensional case, we are going to be using the capital sigma, right, with no square. So this is actually the square of the standard deviation. This is our variance, sigma. And now for the multidimensional, we are going to be using like proper covariances. Yeah, maybe handwriting has like some error on this. But yeah, I mean, please ask any doubt that you have. I think it's better to ask than, regret later. Okay, so let's go now to the multivariate Gaussian. Okay, so I'm just going to start with the mathematical definition. Here we have a term which is even more complicated to remember. But we know that that's not really, you can memorize it or you can just derive it. Most of the times you just need a normalization factor, right, to be a constant, and then you don't use this. But sometimes you might require exactly the exact number. So just to put the formula, well, it's this one. And then, since this is the vectorial form, we need just to expand the previous terms a little. Right. And this thing, right? So this sort of vector. And then, okay, I'm going to write it here. Again, this will also be just represented as this n archaic n, right, where the same thing happens, right? So we have a variable, and then we have a mean, and here, yes, we are just writing the covariance, right? So, okay, so this is going to be the, yes? K, this is the dimensionality. Yeah, yeah. This is number 2. So you see that this normalization factor actually depends on the dimensionality, right? So it's going to be a different number. You can calculate it every time, or you can just use a pre-calculated function if you are like using some software which already does this for you. Or you can just use a normalizing factor. Okay, we'll talk later, but sometimes you might not need to calculate exactly this number. But if you want, it's this one. Okay, I think that was it. So let's give an example of this, right? Because at the end, I want you to get the intuition of this. These formulas are known. I think most of you have done this like in several courses. But let's give an intuition, right, on two-dimensional Gaussians. And for instance, let's say that okay, so we have 0 mean, right, in this. And then we have the following covariance. So what things can we say about this, right? Well, the first one is, imagine that this is, x actually is composed of x1 and x2. Are these two variables independent? No. Yes, okay, so if you remember from yesterday, we talked about the cross correlation, right? And for Gaussians, this is an interesting thing. For Gaussians, I said that, well, what I said is that uncorrelated variables not always are independent. But for Gaussians, that's true. So uncorrelated Gaussians will be independent Gaussians as well. For other distributions, it's not the same. And if variables are independent, they are always uncorrelated. So that means that if this thing is not 0, there's going to be some correlation, right? And let's just write like exactly what this means, right? So this is a two-dimensional function. I'm not going to try to build the 3D thing, but imagine that I'm just drawing here the isocontours and I'm just advancing things. So what kind of correlation do we have here, right? Just like this is approximate, right? I'm going to explain it better. So when, let's say, x1 grows, x2 should grow or should decrease. It should be negative. It's a kind of positive correlation or negative correlation. Yeah, exactly. So why? Because this cross correlation is positive, right? So we don't know exactly how this is going to look, but maybe something like this. So on this class, after finishing this class, you will be able to plot accurately two-dimensional Gaussians, any kind of covariance. Why we want this? Because if you don't see what's happening, how can you really have like knowledge of what's going on, right? Imagine you are doing the state estimation of a position, but you see a strange covariance, and you say, okay, this is it. But actually, it matters a lot. It's not just the mean, right? This is just the first moment. The covariants are actually very important, and with this, you can get like more information on what's going on. For instance, in this case, what we see is that there's a positive correlation. If one of the variables grows, the other is going to grow like proportionally. So positive Okay, let's give a second example, right? So in this case, we have a new covariance, but it's simply like this. Okay, what can you tell me about these covariance? Does it look good? It's not symmetric, so red flag. Yeah, I'm going to put that red flag. Oh, okay. So yes, you are right. This is one of the properties that we discussed, right? So we always need to find for symmetries. If you get a covariance that is not symmetric, then probably you are doing something not very correct at some point. Okay, so we have this. Now, what kind of correlation do you see here? Like when x1 grows, we should be seeing x2 decreasing, right? Okay, so let's say that, yeah, we plot this kind of thing, and then, yeah, well, just hand sketch. Also, these numbers are, well, basically how much you are scaling on each of the factors, but this is just to get an idea. So you see now what's happening when you have like positive correlations. If things are, okay, this, I'm just going to write, what is this isocontour? It's a circle, a line, circle, yeah, okay. Yeah, so it's a perfect circle. You need to use your imagination, but yes, this is a perfect circle, kind of. Okay, in this case, yes, they are also independent. Okay, so this is the intuition. I'm going to explain a little in more detail, right, why I'm writing these isocontours, right, which are at the end, well, values of constant probability, but this is important for having this intuition, right? So this is, I think, a powerful tool. And, well, now I'm going to talk about the covariance projection. Is everything clear with the definition of a multivariate Gaussian, exactly cross correlations, like independence, looking for symmetries? We didn't check, but it also should be positive definite, right? These kind of things are intuitive, right? In 2D, it's easy. In 3D, starts being a little more, for more dimensions, it's not really possible to plot, but all these properties should hold also. Okay, so now also a very interesting topic, covariance projection. This is for the particular case of Gaussians as well, right? So let's say that we have a random variable, right, that is Gaussian. And then we have a second random variable, which is just a function of the first random variable, right? Here there's a full book in nonlinear covariance propagation, right? But here, take a look that this is projection, right? So you are going to see, like, in a minute what we mean by this, right? And let's say that we start with a simple transformation, right? It's just going to be a affine transformation. So, Okay, here, here. But actually, the affine transformation will be important, right? So in this case, f, it's simply a function that relates linearly. Well, not linearly, but relates y to x in the following way, right? So it's not really linear, it's affine. But still, we see like A, it's going to be a matrix, any kind of rectangular matrix that you like. B is just going to be a vector. And this is the kind of transformation that we get, right? So we see what's going to happen with this new random variable, right? We want to say a few things about it, right? So the easy one, it's the mean, right? So we are always, when we start this analysis, we're always going to be doing the same thing. So expectation operator, right? We define it the other way, but this is going to be like basic bread and butter of this kind of analysis, so we always go to the same thing, right? We want to determine this mean, so we start with this. Now, if I'm just substituting what as the function of y, because remember at the end we want to relate this random variable x with respect to I, so I'm just doing this substitution here. And then, okay, so did anyone practice on the expectation operators? You were already very proficient, I guess. Okay, if not, so you'll see. So A is not a random variable. This is a constant matrix, as I said. So you are saying we take this out, right? Yeah. So we can take this out. We can also break down the expectation into two expectations, right? X remains a random variable. A is constant and gets out. And then the expectation of a constant, this is just B, right? So at the end, if we substitute this with respect to the mean of X, we'll get something like this, right? So the mean of Y is determined just exactly with this, right? It's very straightforward. Now, what is the other interesting part? So what is the covariance now of Y? So what do we do? Expectation. Yeah. So let's start just with the definition, right, of the expectation. This is the easy thing. We start with the definition. Okay, it might look tedious, but again, it's going to be very important to be proficient on this. You will see in future lectures. And actually, this will give you like, very interesting insight on how to propagate things, random variables. So what we are going to do, or what is the common analysis, there's going to be, I think, no, you don't need this for problem one, but still, it's interesting. So maybe on the exam you will find like something like this. Maybe, most likely. So the analysis is the same. We just do substitution, right? I'm just here substituting, this is mu of y, right? And then the same thing on the other side. Okay, so far everybody agrees here, right? We are just substituting things. Now we are going to do the same thing, right? So once you have all these factors here or all these expansions, we are just going to combine and do some algebraic manipulations to get things constant out. I mean, to get constants out of the expectation, to group things in a way that we get like known things, right? So this is also very standard. In this case, let me group this, well, I'm going to use a different color. Yeah. So let me group these two A's together, right? So I'm going to take these two things here. So that's what I'm writing it this way, right? So I'm just grouping this thing, and then what we are going to do is here we'll have this term, and it's going to be multiplying to the same term in the other side. Yeah, so this, right? Here I'm just using this property also. This is very useful. You might already know, but this is a property that it's going to be helpful for us when we do these manipulations, right? So the transpose of a matrix is just, just follow this. Okay, you can put here like any number, so B can also be a product of many matrices, but at the end, this property here will be used like in many places. What else? Here, let me do this. Let me just substitute this constant B, right? So we have plus B minus B, right? And this thing goes away. So basically, I'm computing everything, right? There's no term that I left. Does anybody see like something missing? No. Or yes? No. Okay. So then we do the same thing, but now what we know is that this is the definition of the X covariance, right? We take the constant matrices out, and the result actually is this, right? So with this, we have totally determined the Y random variable. This is also Gaussian, right? So from a Gaussian variable X, we apply a affine transformation. The result is a Gaussian distribution as well. And we know that we only need two parameters. Mean, calculated here, and covariance, right? So new random variable, we can write it this way, right? If we want to write it in terms of X, it's going to be this, the mean, right? And this is going to be the covariance, right? So this is covariance projection for multidimensional matrices. Now, what happens that maybe this function is not linear, right? So I just propose here an affine transformation, and things work well when they are linear, right? So it was easy. But usually the world is going to be nonlinear, right? We are going to have a lot of discussion. Actually, most of our problems come from this linearization, right? So if everything was linear, I think there's not really much to explain. But since it is not, this is source of multiple errors, right? So there's going to be approximations every time that we linearize. We need to decide exactly which terms to take into account. But let's now discuss like what is the first approach that we do when we have a nonlinear function. Okay, so this is going to be called nonlinear covariance projection. And okay, let me sketch like this function. It's going to be, again, a function of our initial random variable X. But let's say that in this case, it's not just something like this, right? But maybe something like this. So, well, this is a one-dimensional, just a one-dimensional example, right? So what do we do? Right, I guess the first problem would be, or the first approach would be, we linearize, right? This is always the first thing that comes to your mind, right, when you talk about nonlinear things. So imagine that here we need to linearize, and we need to linearize around a point. Not all linearization points are the same, right? So So for instance, this linearization point, maybe here it's something like this, while this thing, okay, I'm gonna put it something like this, right? So linearization functions actually depend, they are totally dependent on the linearization point, right? So this is gonna be important when you'll see when you basically linearize around a solution, this is gonna affect the quality of your state estimation. The closer you are from your solution, the better. Imagine you linearize, but actually you want to estimate from here, so this is the error you're doing, right? So it's not really great. So linearization, basically, we see that we're introducing some error, right? This is common. But in return, we can use like simple methods that are gonna result in powerful techniques, you will see, and still the trade-offs are not that negative. So let's say that for one dimension, right, I'm just gonna write this linearized function. In this case, we discussed that yes, we need a linearization point, right? So it's gonna be this. And then we need the derivatives, right? Okay, so, well, this is just the first term of Taylor expansion, also known, right? Taylor, does this ring bells? Yeah, everyone, right? Okay. So, and then, yes, we'll have like other terms that are just going to be at least, I mean, square and more higher order terms, right? Basically, this is an infinite series. Okay, so what is the advantage of this? That we'll have this gradient that can be calculated either analytically or numerically, right? And once we have this, we'll see how we can actually apply like our previous covariance projection, right? So, okay, so for one dimension, everything works well, right? But we have already discussed that we are more interested in multiple dimensions. So let's do the same thing, just the first order Taylor expansion of a multidimensional function. How are we on time? Yeah. And dimensions. Okay, so this is the function. Again, we need to evaluate the function exactly at the linearization point. And then instead of just having a nice term, we are going to have a summation of them, right? In this case, D is the dimensionality. This is like each of the variables inside our multidimensional vector. And well, basically here we'll have these terms, right? Oh, tight. Okay, so this summation, actually it's, there's a more compact way of representing it, and it's called a Jacobian. Has anybody heard the word Jacobian before? Right, okay, everyone, okay. Okay, the pen is not working. So I'm gonna try a second pen. And if this doesn't work, then we'll try the third pen, which is on the blackboard. Oh, okay, okay, so it doesn't like something. I'm gonna restore. Very strange. Okay, let me reset. should be fine. Okay. So we are going to do a break now. I'm going to try to solve these technical issues. But hold on. I mean, don't forget about the Jacobian because I'm just going to introduce it after the break. Okay, so we'll be back in 5 minutes. Okay, so let's get back from break, little break. We were talking about this n-dimensional, here the is the dimension, right? Just to clarify in case that there's like some doubt. And then before this break, by technical reasons, we were discussing on the Jacobian, right? And Jacobians are actually very useful when we want to express all these multidimensional problems on a more compact way, right? So in this case, it's slightly different than the gradient operator, right? But so in this case, f is a function that maps from Rn to R, right? And here what we do is the derivative of each of these values with respect to each of these variables, right? So, and this is a row vector, right? So in this case we'll have f. Why is that? Because when we have this row vector, we can actually multiply on the other side by, well, let's say the vectorial form of this, of the x, oops. So this is the Jacobian. So this expressed a little more compactly will look like this, right? So we just have a Jacobian, right? Remember, this is a row vector in this case because f is well, multidimensional function, but still the output is just a real value. And then here we write like the full vector, right? So it's always good if you try to think like in terms of dimensions, right? So exactly what you are multiplying here. So we know that the Jacobian, it's a row vector in this case. And what is this thing? This is a column, right? This x, this delta x. Right, so at the end, I mean, it makes sense. If this is a real value, we need here a real value as well. And then, well, we'll have like some other terms that are just errors, right? But this error, we know that it's bounded. So if we move too far away from the linearization point, the error is just going to become bigger, right? So we'll try to stay close. This is always the rule of thumb. Okay, so then let's approximate this without these high order terms. So let's assume that we forget about them or we multiply them by 0, right? And then what we get is just this known result, right? So this is, here I'm going to expand this a little, right? So I'm just doing this multiplication, right? This is linear, so we can do it. And then let me write it or arrange terms in the following way, right? So we have Jacobian multiplied by x, and then we have all these constant terms, right? So we have the function evaluated at the linearization point at x0, and then we have this Jacobian multiplied by x0. So the Jacobian, once evaluated, this is fixed. This point is the linearization point. So we can say that all these terms are our constant part, same as we defined before. And then what do we need here just to resemble the affine case? That the Jacobian actually is A, right? So this is just first order linear approximation, but the interesting thing is that after linearizing, just the linear covariance projection method that we have explained works well. Well, works. There's going to be like some discussion, right, exactly what is the best way for linearizing, what are the problems here. This is a debate for, I mean, on this field, like that has been going on forever. But for now, this is the first approach, right, the common sense thing. Let's start just with the linear approach, right? And in this case, we can write this way, right? So we'll have the y random variable, which is going to be Gaussian again. It's going to be Gaussian just because we have linearized. If we do a proper random variable transformation using the nonlinear function. This, first of all, might not be like, we might not obtain a closed form, and the second is we don't know if this is Gaussian. But since this is a linearization, we know that for if we apply an affine transformation to a Gaussian, it's going to be also Gaussian, right? So we are very interested now in Gaussians. That's okay. Why? Because they have like amazing properties that we'll see later that will simplify a lot our lives. Is the world? I mean, are all distributions Gaussians? Well, they appear a lot, right, for several reasons. But not every distribution, not every random variable should be Gaussian. So. But okay, this is just the second class, so let's not start with other things. Okay, so this will be the mean, just the evaluation same as before, right? Here, remember that here it was, well, this function here. And then for the covariance, it's the same as before, right? So we are doing a covariance projection, but now just using the Jacobian. Clear? Any question on this? This is going to be an important result that we drawn from today, right? So how to propagate noise. Remember, we are not propagating noise through nonlinear functions. What we are doing is linearize, and then we do covariance projection, right? The other problem, it's more complicated, and sometimes there's no solution. So this is the important takeoff, I think, one of them. So, okay, we have this. It's going to be compact result, right? So just propagating a Gaussian, it's going to still have Gaussians, right? If the initial random variable is Gaussian, which we will provide. And well, basically, there are like a few comments here. So basically, one of them is the errors that we accept, right? Once we linearize, we are adding errors. So we need to know about this. We need to be conscious that fine, we'll make some algorithms. We will adapt some algorithms that are meant for linear systems to work, but we are introducing some error, and sometimes this can be bad. And well, before I talk about different ways of handling this, it's not always like first order terms, but there's other approaches, right? Like non-parametrics, like using particles, sigma points. We will discuss a little on this on the future in this course, right? But for now, linear approximations are kind of, we are already capable of doing propagation of random variables, even through non-linear functions. Okay. So now let's move on to even a more interesting topic, at least more visual. So it's this. Oh, it's not really working very well. So maybe we try to sit there to be closer. Maybe now it's working a little better, but if it fails again, I think yes, I'm just going to sit there because this is a little annoying, right? Being not properly writing. Okay, so visualizing Gaussians, right? We introduced at the beginning this concept of, okay, so can you draw a Gaussian just with the power of your hand and a pen or a pencil? And then, well, we derived like some intuitions, but that was not really drawing a Gaussian. So now we are really draw a Gaussian. Okay. In 2D. Okay. So, well, first of all, some comments. We have already like built some intuition on what it's going to be drawing them, but remember that the distribution of a two-dimensional Gaussian, it's going to look like this, right? So well, this case two-dimensional, but it could be more. And then what we were plotting before is isocontours. So what does this mean? So basically what we were plotting is all these values, right? So we were plotting like P of x for all these such that P of x is equal to, well, it's basically constant, right? Okay. And then there's basically different levels of this, right? So this is a little, no, actually I'm gonna erase it because this is not right. So what we are plotting is x, right? All these x that belong to the same, that have the same so we were plotting this before, right? But okay, maybe I should write things properly, right? Like I'm not gonna try to go so fast. Okay, so just things written slowly and clear for everyone. So then if we want to look for constant values on this probability, right, basically what we see is that it doesn't matter that here there's an exponent, right? What we are looking for is that constant terms in for this, right? So if you do the derivative, still the value is the same. And if you do the logarithm, excuse me, the value is still the same. And then what we are going to be looking for is that this exponent, it's going to be constant when we satisfy this condition, right? So k, it's going to be a number. We'll see later what it is exactly. And basically what we want is that this exponent that I'm writing here, removing the, I mean, when you do the minus logarithm, this sign goes away. And the only thing that stays are these, right? This is also called, well, Mahalanobis distance. I will define it later. But, well, basically, we are looking for all those values, all those x, that satisfy this condition. Now, in this case, we can say that k can be like an integer, right? So it can be 1, it can be 2, right? And for each of these values, this will correspond to 1 sigma. So k1 will correspond to the isocontour of 1 sigma. k3, it's going to correspond to the isocontour of 3 sigma. Okay, well, you can derive this if you work a little, at least with the one-dimensional case, right? So you will see that, well, the value, the only way that this is true is when x actually is the standard deviation. So let's now plot the 3D thing, right? So the isocontour, it's going to be this, right? These lines. And we know that these curves are actually ellipsoids, right? If the covariance is no, not diagonal. If it's an identity scaled, we know that this should be like a circle, perfect circle. If it's diagonal, we know that it's going to be an well-aligned ellipsoid. But in general, this can be any kind of ellipsoid, right? So not aligned. So that's what we described before with the correlations. Right, and then basically we're interested in this, right? So the circle of this line, it's going to be this k multiplied by the standard deviation. Again, this is just intuition, right, for the one case, for the one-dimensional case, but it's going to be something like this. So for 2 dimensions, it makes a lot of sense to write these things. For 3 dimensions, as I said, yes, we have like ellipsoids. For more, well, it's hard to visualize this, but I think you lose intuition once you move to more dimensions. So that's always something that we should be doing, right? So select exactly which dimensions we'll be plotting. I will talk how to remove some variables. So this is also called marginalization. How to remove them properly, and then you will visualize. This will happen next class. But for now, let's say that we just have 2-dimensional variables, right? Okay, I also talk about the Mahalanobis distance. This is not just useful for drawing isocontours, like curves with the same probability, but this will actually appear in many other derivations, so especially when we optimize over Gaussians. Okay, so we are just going to follow this notation, right? It's regular distance. It's not exactly the only difference with like L2. In this case would be that here we are adding like these covariance, right? So exactly what we mean by this is that inside this, oops. Oh no, okay. Yeah, it's not the mean, it's another any value. So what is happening inside is instead of just having an identity, which is what you have, right, for L2 distances, we'll just have the inverse of the covariance, right? So what is this really doing, right? It's kind of weighting each of the dimensions with respect to its uncertainty, right? So again, this will appear later, but now, just for us, this distance has been defined, and then when we refer later, you'll say, oh, but this is just this, right? So standard distance with the covariance. Actually, since we write all the time this covariance also here, you will know that we are talking about this, right? But this is not L2 distance. Yep. Yes, this is why. This is, yep, my muscle memory. Okay, so then what is going to be the problem, right? We want to plot this. Right, and for non-spherical, that means for covariances that are not exactly identities scaled, it's not going to be so clear, right? What is this distance, right? So we need to find this. So what we are going to do is very simple, right? Let me rewrite again the affine transformation. In this case, we are going to be using an affine transformation. And what we are going to be saying is that X, it's just going to be a normal distribution with zero mean and just the identity as covariance, right? We know that how can you generate this? It's very simple, right? You can generate this very easily. So the problem then it's going to be fine. The problem is going to be the following. So we want to find the matrices A and B such that the distribution that we want to draw correspond to that, right? So this is going to be like a little inverse problem. Instead of just doing covariance projection, we are going to find the parameters that gave us the distribution that we want to plot. Okay, so basically, so we have a target covariance, right? And then we are going to be looking for this. Mean, remember, yes? What is the covariance? This is the identity matrix with zeros, zeros, right? Okay, so which symbol do you prefer? This one? Yeah? Okay, okay. Okay, how I'm gonna delete this? Almost. Okay, and now I'm deleting this. So we have consistent notation. I think this is important, but I also want to talk the same language. So we have here this identity. In this case, this is 2 by 2. Okay, what can you tell me about the mean, right? So if the mean of X is 0, it doesn't really matter, right? So this is just gonna be B. Right, so for the mean, it's kind of easy. The only problem is on finding this. right? So let me formulate then the problem this way. Again, just with words. Problem, find A such that projects into this distribution, right? And what we know is that the distribution of X, it's just going to be the identity. No, the covariance of X, it's going to be the identity, and it's zero mean, right? So this is the most simple distribution that you can find. Okay, the problem is clearly defined. No? We have phases of, okay, what is this? Okay, so maybe we keep going. Let me now expand this a little, right? So we also know that I'm writing this, but actually this is the identity, right? So what we are looking for is a matrix, any matrix, we don't have any idea, such that it decomposes into, I mean, we have this. We have this we have. We know. We just need to find a factorization of this covariance that is going to give us this matrix A, right? And this is what I'm introducing, like 2 ways of solving this. Probably you have heard about this, but well, just again, I guess, just presenting them for this particular problem. So the first one is the SVD decomposition, right? So we know, or we could also here be using the eigen decomposition. We know that the matrix, the covariance matrix is symmetric, right? So in this case, and it's positive definite. So SVD and eigen decomposition are the same decomposition, right? So this is great because our covariance just happens to have these properties, right? So to eig, because no, it's symmetric and positive semi-definite. Okay? So, okay, let's say that we are just using the SVD. Right? So we have this matrix. This is the distribution that we want to plot. Right? We know that the mean, it's not really going to be a problem. It's just going to be this B parameter. Right? So it's going to be translating our Gaussian into any point in the plane. Now, what happens with the covariance? We have this number. It can be as complicated as you want with, I don't know. Well, it's still a 2 by 2 matrix, but so we have this, right? We said that actually this is symmetric. And then, so this decomposition is clear, right? For everyone, you are orthogonal matrices. These are diagonal matrices of real values. Yes, so the composition, this is the first time we're introducing SVD, but did you heard about this? So people doing linear algebra, yes, others. Okay, anyway, so it appears in many, many problems. In this course, yes, we are also going to be using this. And then what we are going to do is just separate this a little. We know that since these matrices are diagonal, we can do this very easily, right? So you have a diagonal matrix. Let's say that we separate this in 2 terms. And I'm just writing it this way because it's going to be more convenient. But what I mean by this is I'm calculating a square root of a diagonal matrix, right? For now, let's say that you just care about the diagonal, so you don't have to do much. And then I'm using here this transpose. We know that the transpose of a diagonal is the same thing, right? But let's just keep this transpose, right? And then we have ut. But the interesting thing is that now what we have is exactly a square form. So if you say this is going to be your A, right, in this problem. So this is the projection that you are looking for. You have your mean, you have your covariance. Then what you do is you just run SVD. This is approach number 1, by the way. And then with the matrices that you get, you simply multiply the square root of the diagonal on the well, on the diagonal term, and then you multiply by u, right? So this is going to be your A. You have this, and you are done. So then when you want to generate your any kind of distribution that you want, you just generate it from the x, which remember, it's going to be, okay. Yeah, I think I need a table. So we are gonna be drawing, yes.
You mentioned that we use two conditions, that you have symmetric matrix and positive symmetry.
Yes.
About symmetry, the property of symmetry, but how do we use here for the property of positive symmetry?
No, you don't use it here. Well, so first of all, you need to be positive definite because you don't want to do a root square of a negative number. I think this is the first one. And the second one, what I said is that if they are symmetric and positive definite, SVD and eigen decomposition are give exactly the same result. So it's not that we are using it, right? So far, it's not a requirement. You need this because if you have like negative numbers here, it's going to be non-defined, right? The diagonal, you cannot do a square root of but at the beginning, what I said is simply that. You can just do eigen decomposition because it's the same when these two properties are met. Yes? Yeah. So, no, it's because it's symmetric. Positive definite has nothing to do with this. So if you have the only way to this factorization to hold, right? If you want to have like this should also be symmetric, is to have the same kind of orthogonal matrices in both places. Okay, so far I haven't really used the positive definite version, but I'm going to use it now on option 2, which, by the way, it's our preferred option, right? I'm going to write here a star. Okay, so there's a very interesting decomposition, right, which is called Cholesky decomposition. Right, you can only use this decomposition when you have positive definite matrices. Right, so in this case, yes, you need exactly this because if not, for SVD, it's not required, right? But for the Cholesky, yes. And then what is the advantage of this? That if you run this decomposition, right, this is again our given covariance that we want to plot. If you have this, then it's going to give you exactly your result. You don't need to multiply anything. You don't need to multiply matrices just to get this. So the result of the Cholesky is this. Two matrices that are equal, right? This is in this case lower. So we have here a lower triangular matrix. This is zeros and this is something. And okay. And this is the transpose, right? But the two things are the same, right? So you multiply them and you get this. What's the good thing about this? That this is exactly what we were looking for. Because then later, your I, it's just going to be this, right? You multiply all your samples, and that's it. Let's give an example. I have an example. Okay, so I'm just going to give like this covariance, right? Right, and the problem is let's draw the isocontour for k equals 1, right? So this is the 1 sigma isocontour. So what would we do? Right, so I'm just gonna do, the Cholesky algorithm. There's like a proper definition of the algorithm. There's a lot of theorems on, well, there's a very interesting one that I'm gonna comment later. But basically for a 2x2 matrices, we can start doing this just by hand. Or, mentally, right? So we know that we are going to have a matrix that looks like this, right? So this is a value, this is another value, this is a 0, and this is another value, right? And the same happens for the second part. So we have exactly the same matrix. So here we have AC, and then what we have here is this thing transpose, right? So in this case, this will be L, and this is L transpose. Okay, everybody agrees on this? So given this initial covariance here, we are going to find which is this factorization, right? So it's simple to calculate because you'll see, so there's methodology for doing this, but because we have these zeros here, there's basically, so this is, okay, so for those of you that have already done linear algebra, you know, right? So this is a iterative method where you just keep growing boxes, kind of. But if you want to do this 2x2, it's easier, right? So we know that this thing is going to be equal to this matrix, right? And then which is the first multiplication? What is the first term that we can calculate very easily, right? Remember that we want to exploit zeros. So it's going to be this component, right? Because this component is this, right? It's this row here multiplied by this. So we have a 0, we have a 0. We know that 4, right, should be equal to this. Right, I'm just doing matrix multiplication, 2x2, nothing crazy. Again, there's a formal definition of this algorithm that grows incrementally, but if you start doing this 2x2, this is the first thing that you would do. You go to the top of your matrix, you exploit the fact that you have zeros there, and then this is absolutely well defined on this. And then what we know is that A actually should be plus or minus 2, right? And here comes the theorem, right? So if we define the diagonal to be positive, then this Cholesky decomposition is unique, right? And this is also going to be useful, right? Because it doesn't matter actually what we change in the algorithm. If the diagonal is always positive, this is going to be unique decomposition. So what do we do? Well, we choose positive, right? Just to keep the yeah. So let's keep this. Okay, now let's go to the second variable. Careful that I don't lose this. So what is the, now that we know, this is just substitution, right? At the end, this is not much more complicated than a linear system, but the second variable that we can define, we need to find like some zeros, and for instance, it could be this, right? So B multiplied by A, so this multiplied by this should be equal to minus 2, right? So in this case, B multiplied by A, or if you want, we can also obtain this number, right? So we can go here and do this multiplied by this. So we have A multiplied by B plus 0 multiplied by C, so C goes away. So this is also a good thing, thanks that to the symmetry, right? So BA equals AB. This should be minus 2, right? So then we have the second term. Okay? And then we are going to do the third term. For the third term, there's not really much we can do, but we already have the value of B. So it's going to be B squared plus C squared. This should be 10. So that means that C, right, we just take this out. B is going to be minus 1. Oh. Right? So we have the same ambiguity. So the diagonal is always the same. We need to choose positive values. Right? So as I said, diagonal positive, and this exists just a unique decomposition, right? So this is great. Okay, so in case that you were not convinced that this is actually working, let's say that we have now let's say that we want to project this actually into a real plot, right? So what would we do, right? Remember that we have this matrix, this is L, as we have just calculated here, right? Remember, A was 2, and this is the number. And then what we are going to do is very simple. We are going to plot a circle, right? So if we plot a perfect circle in X, right? This is for the random variables. Then we multiply by, every point in this circle that it's easy to calculate points here, we transform by this AX plus B, and then we'll get our strange or whatever covariance it is, right? So in this case, can someone give me a point that we could choose here from this X distribution? This, remember, the isocontour is a circle that we can project. Okay, so 0, 0, that's not a good point, right? So what are the easy points, right? So let's say that this is the 1 isocontour. That means that this circle is radius 1, right? So 1, 0, right? Or 0, 1. These 2 points are in the circle. Remember, what we have here is a circle. We are going to rotate it, or we are going to translate it, and then we are going to scale it and rotate it. Right? So it's basically, the idea is that this perfect circle at the beginning is just stretched in different ways, right? And this depends on this L matrix. So here we can start with this, right? 1, 0, right? So I'm not doing anything crazy. I'm just transforming a point in the circle, right? So we can maybe transform 4 points. And with this, we'll have like some coordinates, right? So if we transform this, we have here 2, 2 here, and here we have -1, -1, right? So we know that this is a point that it's going to be here, right? So x2 and y -1. So this is one point that it's going to be here. Also, what else can we say about this covariance? That the correlation is negative, right? So you see cross correlations here are negative. That means that kind of the shape, it's going to be in following the -x line, right? So we know that it's going to look a little like this, right? So just to have, but this is a point that belongs here. What other point we have? So now it's not 1, 0. Yep. But let's say that we transform 0, 1. Okay, so we do exactly the same thing, 2 multiplied by 0, 0, 1, so we have here a 0, and then here -1, 0, here we have a 3. Okay, so this is another point that belongs here. 1, 2, 3, 0, 3. Okay, so now the question is, can you draw, like, if I give you any covariance, can you draw, like, what is the isocontour of it? Can we? So we have 2 points. We know that it should have, like, this kind of form. So let's say that, yes, we come here, we do this. On the other side, it should be symmetric. Okay, so it's a little better, but at least it's not, like, approximate. We have exact points in this if we do the same for, let's say, -1 and 0, -1, this will also give us like valid points inside this new isocontour. Okay, I see a lot of strange faces. The question is, with this, we should be able to draw any isocontour that you want, right? So given any two-dimensional variable, right? So can you draw the isocontour? Let's repeat again what is the methodology, right? So what we are going to do is just affine transformation. We are going to define an auxiliary variable that is, this is 1, right? Just a perfect circle, center at 0, right? So we have a circle. Now, with this variable, we are going to say, fine, we need to find a transformation such that this y variable, right, gets multiplied by some matrix and gets some summation, right? So this is the affine transformation. It's going to be transforming this to get the result of this, right? But we don't know. These guys are to be calculated, right? All we know is that this is the target covariance and this is the target mean. Okay? Now, first step is mean. So since we know that the expectation of this, it's going to be this multiplied by the expectation of x plus b, but this guy is 0, right? Our mean, it's going to be very simple. It's going to be b, right? So we know that b, it's going to be exactly this. Clear? Okay, so it's going to be basically this. The intuition is how you are transforming, how you are translating. So if you notice here, I didn't plot. I didn't plot here the center, the reference frame. So I didn't plot here 0, 0. It's because this is not 0, 0. This is the value of the mean, right? So I'm just translating things. Yeah, translate. So mean is clear, but now what about covariance? And this was the only thing that was a little complicated, right? So we know that we are going to have this, and this is going to be equal to the covariance that we want. So we need to find any matrix that actually has this. And we know that since this is the identity, it's going to be this. So because we have this, we know that we can either use Cholesky, because Cholesky is exactly giving you this. So we have a positive definite matrix, symmetric, so covariances have this property, so we can use this factorization. Okay? So then if I'm asking you, okay, so can you plot it now? You will say, sure. Just give me any, well, let's just define like this circle, this function, which is going to be affine, mean, it's going to be absolutely trivial, right? So you just take the mean to be this b value on the affine transformation, and then covariance, it's just, you just go there, do the factorization, and that's the transformation, right? And then what you do is you define some points, right? So you define like some x that are inside this isocontour of the circle, right? 0, 1 was 1 point, 1, 0 is 1 point, square root 2, it's another point, but maybe that's a little more complicated. So you have like a set of points, right? And then all you do is just transform them with this, right? You have like key points, and then you draw a covariance. Okay. Is it now more clear? This is going to be in the problem set. But I think this is essential, right? We need to draw things. Unless we don't draw things, mean is not enough. It will never be enough. You need to know what are the covariances. So for higher dimensional problems, okay, you take a look at this, maybe you take a look at the determinant, information, entropy. There's many things there, but for two-dimensional things, you draw them, right? This is the best way of debugging things visually. And if you can, okay, then you need to get other solutions. But this is very something that you will be using, not just in the problem set, but later. Yes.
How many points to recover this?
So this is just an exercise for drawing still by hand. In the problem set, I suggest to use 30 points. But you are not going to do this by hand. So by hand, you can calculate 2. And then you know that there's symmetries, right? So the one, it's going to be just minus, for instance, this 0,3 was actually 0 minus 3, and the 1 minus 2 was in the same thing. No. I'm just talking about points. So if you just multiply this guy by this, right, you are just multiplying the whole thing by -1. So that means that you are going to have here this, right? So this is what I mean by this. You can calculate points, but you just need to multiply by -1, and you have still a point in the isocontour. So with 4, I think you have a lot of information. And then you kind of plot it, and this is much more accurate than just, drawing things without really knowing much. If you plot 30, it's going to look amazing, like perfect. If you plot more, then yeah, better. But there's not really need. Because this is a requirement for the Cholesky decomposition. This only works if you have a positive definite matrix and symmetric. So it's very interesting. If not, what you usually use is just LU decomposition, right? So in general, this is more general decomposition. But for this kind of particular matrices, which are covariances, with these very interesting properties, then we are going to exploit like these properties. And that means that the methods for the decomposition are going to be more efficient than, let's say, just use SVD. Okay, Cholesky will see that it's more efficient. And it's going to be even more efficient when we do this for higher dimensional and sparse matrices. You will see. Okay, yeah, but it's a good comment. So why use? Yes, we have another question. It's the center of reference when you are plotting these new covariants, right? So if you want to think about this as center of reference, yes. But it's just how you are translating. So you are drawing this ellipsoid, you need to translate it somewhere in the plane. Okay, very good. So what else can we do, right? We have kind of explained how to sketch this, any covariance into a plane, into a paper. This is also useful for you to plot like ellipsoids, right? I don't know if you're running a program and you want to see exactly what is going on. So this is useful. There's another useful thing, which is going to be sampling, right? So for sampling, we have exactly the same problem. Now it's not about drawing isocontours, but we simply want to draw any distribution, any Gaussian distribution, right? And what we know is that, well, maybe our program only gives us like one-dimensional normal distribution with 0 mean and covariance 1, right? So this is the starting point. How to generate from this simple random generator like a proper distribution, right? Any distribution that you want. Well, any Gaussian distribution that you want. I'm sure that many of you have already used this, maybe on a different way, but sampling, generating samples, it's like common thing, right? So maybe it was on different ways, but just following with the same explanation, you will see that this is actually just covariance projection again. Sampling from Gaussians. Okay, so as I said, this is the initial condition, right? We have a lazy program which only gives us this random, it's still a lot, right? So I had to write before, like from a uniform distribution, how to generate a normal distribution. So basically there's a function for that. I think no program anymore does this. So you have, yeah, you have normal distributions everywhere. But before it was even worse because they were uniform distributions, right? So this is actually what is happening like on the low level. The random number generator is not normal, it's uniform on machines, I mean. Okay, unless you buy more sophisticated things. Okay, so let's say this is the initial hypothesis. We have a random number generator that gives us this distribution, 0 mean, 1 variance, right? And then the problem, now we are going to any kind of dimensionality. This is, so for drawing, it's true that we are kind of constrained just to the two-dimensional case, but for sampling, it can be any kind of dimensionality, right? So the problem is how to sample a distribution, right, that we know that we want. We know the mean. Oh. Yep. And we know this covariance, right? So this is just a distribution that we simply happen to know. It's a Gaussian distribution. We know its mean. We know its covariance. It's perfectly determined, but we cannot draw it, right? Because our language program doesn't have a function to draw multidimensional variables. By the way, does this Python already do? If you just put like any kind of dimensional mean vector and covariance, it plots? Is this like some package? There is. Okay, anyway, this is still useful. Yeah, so maybe in some years it will not be necessary to do all this. It will be happening. But what will be happening in these functions, it's going to be what we are going to be explaining here. Right, so again, we are going to be using covariance projection, right? And the steps are going to be the same. So the first of all is we just select the distribution, right? So in this case, now the question is, if you have a multidimensional vector, how can you do this with a single random number generator? So it's as simple as just draw different samples, right? So you go for each of the components, and you will have here this, right? So you draw this for the first variable. You draw this for the second variable. Oops, this is a 1, right? So this is what you have, just a call to this guy. I mean, I know that now you can sample like vectors, but, well, basically inside this is just n calls to the random number generator. Right? And the idea behind is that these samples should be independent and identically distributed, right? So they are independent, more or less. I think for what we want, yes, they are independent. Maybe for cryptography they are not so good, but still good enough. And basically with this we create a vector, right, of all our samples. Now we have created this multidimensional vector, and the thing is we are going to define this function, this random variable, all these samples are going to be defined with respect to the random variable x, right? So we know that if we do covariance projection, it's going to look like this. Right, so this is the result that we discussed at the beginning of the class, right? So this is standard things. Here I'm not assuming anything about the mean of x, which we know it's 0, and I'm not assuming anything about this covariance, right? But we know that if we do this, it's going to be the identity, right? So if we start like doing things, the first thing that we can do is the following. We know that this goes away, right? Because this is 0. So that means that be, again, no surprise, it's just going to be exactly the mean, right, of the distribution that we are trying to sample from, right? And then we have a third step that we need to find A, right, such that this property is satisfied. So it's the same thing again, right? But this can be any dimensional. So again, we are just going to be using Cholesky. Okay. And then what do we do? Well, we just draw samples from this vectorial form, and then we just multiply this, right? So the result is going to be this. Now remember that this A or this L, well, it depends on what you want to write, can be any size, right? So it's not just two-dimensional. You can be drawing like any kind of covariance that you want. So, and that's it. So with this very simple normal distribution that you have a call in your program, right, you can generate any kind of Gaussian that you want, right? Now this is not limited, so to just 2 dimensions, right? This could be any dimension that you want. So you just do this, multiply these samples drawn like this by this transformation, you add some value, whatever mean you are looking for, and with this you can generate this number of samples. Cool. So it's clear, this part. I mean, any questions, please, thumbs up. I'm going to repeat it as many times as we need. Because yes. No. Well, yes, but this is also known as the Cholesky decomposition. So you could formulate this as a linear system, as I was doing, just putting each element, and this is kind of equivalent problem. But in general, and this is going to be true for this problem, when you have more dimensions, you want to follow some methodology, and there's an algorithm for the Cholesky decomposition, right? So basically, it's an incremental algorithm. But it's equivalent to solving like linear equations for each of the components on the matrix. This is done, so I'm just going to ask you to do this for, in case that you want to draw things like in the paper. But if you are running your program in problem set 1, you have Cholesky decomposition. Absolutely use it, please, because it's going to be more efficient than any handwritten thing. Okay, so how many of you, I'm just curious, how many of you were already familiar with these transformations on sampling? Many people, right? Okay, so now we are all in the same page, right? All students. For this, what you see is that you need to be proficient with expectations, right? There are some decompositions, but I think now we have introduced them, so now they are known to everyone. And with this, I think you are able to finish big part of problem set 1, so please start. And next day, we'll talk more about Gaussians, right? So next day, I'm going to talk about marginalization and conditioning of multivariate Gaussians, which is going to be also very helpful when we describe the Bayesian approach for filtering. Okay, there's nothing that you should be checking now, but in the future, I'm going to ask you, oh, please, for next lecture, take a look at chapter 3 in probabilistic robotics or in Barfoot's book. But for this, I think it's fine. Just take a look at the hand notes, and we are going to do the derivation next day. All right, see you all in Thursday.